So welcome to the session, and today I came with a new session of matrix. Before we go further, and we will deal with the basics of matrix here, in the sense that we'll see what exactly goes inside the matrix and what exactly the operation means to us. I'll also cover the very essence of eigenvalue and eigenvector, which is the primary focus of today's lecture. So before we go further, let's ask a very simple question. And the question is 2 into 3 is what? As you can see on the screen, clearly the answer is 6. What does it mean? Let's say if you have 2 apple into 3 apple, does it mean to have 6 apple square? Not that bad, because we are used to have the notion of the mathematical structure like 2x into 3x goes to 6x square. Okay, 2y into 3y goes to 6y square. So why not 2 apple into 3 apples would give 6 apple square? But it doesn't feel digestible, right? So we have to ponder a little bit more inside this. Basically, when you multiply two numbers, it's not like we are talking about both of them as an object. Here, multiplication itself is not an object. It behaves as an operator. To understand this in a very simple language, let me rephrase the question to convince myself what does 2, 3 and 6 exactly mean. So now I ask you a second question, 2 apple into 3. And that makes sense because multiplication is even repeated addition. So when I talk about 2 into 3, it might feel to add 2 apple 3 times or vice versa 3 apple 2 times. And that's quite convincing. So here we can clearly see 3 behaves as an operator. So 2 apple into 3 equals 6 apple. Now it makes more convincing sense, right? So here 3 is behaving as an operator and this 2 apple behaves as an object. So an object with the interactor of multiplication using the operator 3 gives the result 6 apple. I hope I'm not complicating the thing, because it will be the same mathematical idea, the same genetics will be executed for the other mathematical structures and will come soon to matrix. Let's try to see in the other way. What if I would have taken 3 apple as an object and 2 as an operator? Needless to tell, you'll get the same answer. And this is fundamentally the commutative property of the product of two numbers. So whether it's 2 into 3 or 3 into 2, they are equal in that sense. But we can't just stop here. What we have 2 into 3 into 4, does it make any sense now? Clearly, if you associate an object to all the 3 multiplication, 2 apple into 3 apple into 4 apple, it makes less sense. Why? 24 apple cube feels like the apple is projected in a 3D space. So when you are multiplying apples, clearly you are not making a juice out of it until you define so, right? So here again we can imagine 4 apple to an object and 3 as an operator and 2 as another operator. So now again, it depends on the rule of the game, like how we define it. So if I use associative property of the numbers, which I'm tempted to use it, imagine if there would have been no associative property, still I will be tempted to follow my basic principle of counting and will be tempted to write 3 into 4 apple as 4 apple interacting on operator 3, that gives 12 apple. And again we have a second operator of 2 which operates on 12 apples to produce 24 apples. So far so good. So it makes sense. The takeaway from the story is very simple. When we are multiplying numbers, the multiplicand is not always object. Or to get the feel of the situations, we must introduce the idea of, in fact, the fundamental idea of operator and object. So now we have a very strong way of looking at matrix from the point of operator and objects. Under what circumstances we are going to see something as an object or operator that depends completely on my perception or completely on the project or on the problem or a statement of problem solving, right? So here we start with the basic idea of matrix. And I'm sure like all of you are already acquainted with the basics of matrix. And I'm sure that since all of you are already acquainted with the basic of mathematics, in one of my video, I'll be discussing about the motivation behind product of matrix. So why matrix are multiplied the way they are multiplied. So is there any natural thirst of multiplying that? Is that a natural consequence of some operation or some mathematical structure, or is that just a cosmetic definition? Clearly, it cannot be just a cosmetic definition. So there must be strong motivation behind that, which will be discussed in one of the subsequent lecture. For now, let's be focused on what exactly operator and object means on matrix. And here we go with our first fundamental idea. As you can see on the screen, if I've got an identity matrix 1001, the name identity is derived in the sense like if I multiply with an object, let's say ME. So as you know, when we multiply into matrix, so the first row will be multiplied with first column and second row will be multiplied with second column, and it's basically dot product, right? So 1 0 will get multiplied with ME, that will produce M. 1 times M, 0 times C. 0 1 will get multiplied with ME, that will produce E. So here result of operation on the object is unchanged. So me becomes me, you is still you. Hence this operator is preserving the identity of the object, and hence it has derived the name identity matrix. Let's have some more fun and let's take another matrix 2403. This will be our friend for a long time. So let's see what exactly it does. If I perceive A as an operator, it will do something. If I perceive A as an object, then it's just a collection of objects. It may mean like we have 2 apples, 4 oranges, and other guys having 0 apple and 3 oranges. But that doesn't give a nice visual description of this matrix when you view it from the object perspective. Rather, let's view from the operator perspective. So what basically A does to me? Let's see what it's doing to ME. So if you multiply this matrix, in fact I'm pre-multiplying it. So as far as the law of matrix multiplication is concerned, we'll get 2M plus 4E and 3. Oh, that's cool. But what does it do to 1, 1? Okay, so let's see. So again, we multiply with 1, 1. We are getting the answer 6 and 3. So what does it mean? What does it mean to have 1, 1 going to 6, 3? So this behaves as an operator. This matrix behaves as an operator. 1, 1 is reacted with this operator, and finally we got the result of 6, 3. So let's move further and try to get a feel of this. Let's say if I represent 1, 1 on XY axis, for the same reason you could have told like it's 1 apple, 1 orange, and you have apple axis and probably orange axis. So this matrix, what it's doing to 1 apple and 1 orange is basically it's getting converted magically to 6 apple and 3 orange. Isn't it interesting? So you can run a good business out of it. Anyway, so 1, 1 is getting transformed to 6, 3, and hence I'm rotated and scaled. So not only 1, 1 is scaled up, but it's also suffered a rotation in the clockwise sense by some angle theta naught in the language of mathematics. And clearly you can see the length of this vector from root 2, it has changed to root 36 plus 9. Right? Okay. So far so good. So here I have, for the sake of clarity, I have made input in black color and output with the other color, orange. Now let's have little bit interaction with more members of the society. Let's say 1 0. So what exactly 2 4 0 3 this matrix A does to 1 0? So 1 0 is here. We have 1 apple, no orange, and the result is very obvious. We'll get 2, and by multiplying 0 goes to 1, 3 goes to 0. So 1 comma 0 is just scaled. 1 comma 0 is just scaled and no rotation. What it does to 0 comma 1? Well, so 2 4 into 0 1, that will give you 4, and 0 3 into 0 1, that's going to give 3. And very surprisingly, 0 comma 1 is not just scaled, but it has also suffered a rotational change, because 4 comma 3 will be somewhere here, right? And as you can clearly see, we have initial object here and the final object went to other place. So in fact, there is still a clockwise sense of rotation, whether it's 1 comma 1 or 0 comma 1 or 1 comma 0. For them, for 1 comma 0, the rotational angle was 0. For 1 comma 1, we'll have some non-zero rotation angle, and same for 0 comma 1. Okay, so this is just experimentation. Like we have a matrix A, we try to react with certain objects, and we are getting either rotated or some linear combination of these objects. Okay, something has plus something star kind of this. I call it linear combination because the coefficient is feels like something x plus something y kind of a structure, and that's why the name linear algebra. Anyway, now here is a big question. The question is, let's say I'm interested in all the family members of those apple and orange pairs which does not suffer any rotation. So we want only a scaling of orange and apple pair. No rotation should be there. So one such answer, as you must have noticed, is 1 comma 0. So if I have taken 1 comma 0 as an reactor, so the final reactant that we are getting is just scaled, right? So this is an operator, and we have reactors and reactant. Operator is fixed during the course of the problem. Reactor keeps on changing, hence reactant will also change. Okay, the final product will also change. So now let's talk about who am I such that the members in my family doesn't suffer any rotation. So I don't want basically dizziness, right? Because you can feel like if you have rotated, you will start feeling dizziness. So can you help these apple orange pairs as a mathematician? Hey someone, where's my family? Please let me have a look at them. So let's try to solve this question as a maths guy. And here we go in a very basic style. So we have a matrix 2 4 0 3. Let's say that unknown guy is x apple and y orange, and we want just a scaled up version. So I can tell it simply lambda x and lambda y. So my point is, if I take any ordered pair of apple orange, I want it to be just scaled along the same line. So maybe I'll end up here, or even I can end up this smaller chunk, or I can go in opposite direction. Wherever it will go, my line of action must be along this. So I don't want xy. I don't want xy to suffer any rotational change. I don't want apple orange pair to get rotated. So how many crazy pairs of xy exist? One such example we have already looked is 1 comma 0. So are there infinitely many? Are there infinitely many? You can soon realize, like once you know the answer 1 comma 0, any other answer along this line of action will also work. Let's say if I take a point 2 comma 0. So what, instead of multiplying with 1 comma 0, I would have multiplied with 2 comma 0. So the result is not much surprising, because as you can expect, like 2 is just multiplication of 1, so it will also not suffer any rotation. So we'll have 4, and this guy still goes to 0. So 2 comma 0 has went to 4 comma 0, right? So in that sense, I can have infinitely many vectors along x-axis which will not suffer any rotation. So you might be tempted to tell there is definitely infinite answer, so there is needless to count any further answer. But the point is, we want different directional answers. So we know like one of the answer will be along x-axis, right? Now clearly we can have different directions. So we can have direction number 1 where we found the answer, direction 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. So now your question boils down to fundamentally how many such directions are available, where if you pick up any apple orange pair, the final product will still be scaled on the same direction. So it's not going to change. So one such answer I have found along x-axis, right? So along the direction of I cap in language of vector algebra. So is there any other directions? Let's try to find. Instead of playing with some random numbers, we can just come with the general values of x and y. And let's try to find for what x, y, x comma y is scaled to lambda x and lambda y, where lambda is a real number. So it can be positive, negative. Okay, can it be 0? Can it be 0 for all x, y? No, because if it is 0, then matrix A has to become a null matrix, right? That also you can do very easily using matrix multiplication by setting up a equation. Now if I want xy to get scaled up in this fashion, so I want some xy, I want it to get scaled up, clearly you can see I can little bit arrange this equation. So 2, 4, 0, 3 xy is, so now if I want this to work, so now if I want xy to be scaled up in this fashion, clearly you can see we can expand this equation. So this I can write in a very simple way. 2x plus 4y, and we have another multiplication is just 3y. That must be equals lambda x and lambda y. And this is your basic system of two equations. 2x plus 4y equals lambda x and 3y equals lambda y. Needless to tell, this equation can be handled in a very simple way, where I can write 2 minus lambda x plus 4 equals 4y equals 0, and you have 0x plus 3 minus lambda y equal to 0. There is a reason I am writing like this, because I want to generalize it soon. Now if you want non-zero solution, why I want non-zero solution? Because I know if I keep xy 0, so if I am at this state of no apple, no orange, no matter with what matrix you multiply, so 8 times this matrix will always be 0. So if you have nothing, you will stay at nothing. So you must need to have something in order to start with in your life, so that you can accumulate further, right? Okay. Now if I want a non-zero solution, of course that I'll be tempted to do, because for every 0 comma 0 will definitely be a solution for this equation. So for x comma y to be different from 0 0 pair, we know the det of its coefficient must be 0, okay, for a non-zero solution. And this thing you can derive again from fundamental of class 7, 8 logic, because you can just put x in terms of y and find the value of lambda. Okay, so a cool way is using determinant. So if we calculate this, from here we are getting two values of lambda, 2 and 3. So now we have got, like, we can't have more than two directions. And of course, one of the direction which we already know was the direction along x-axis. This was from experimentation. So now we have to find just one other direction. So we can't have any other direction apart from this. So this is not allowed, this is not allowed, this is not allowed. So we know since we have only two values of lambda, so there are just two directions along which the apple orange pair will just suffer a scaling change without any rotation. So let's have the discovery for that. So now we try to calculate those directions. So direction calculation along which there is just a scaling change. So let's put lambda equals 2 in the equation and try to find x and y. Again, since we have already a system of equations generated over here, so what I'll do is just I'll use this relation to find x and y. If I'll keep lambda 2, we'll get 4y equals 0 and y equals 0. And that should not surprise you, because y equals 0 is already representing a line along x-axis, direction along x-axis, right? So what does it signify? It signifies, like, if I'll take up that matrix A and I multiply with any x apple and 0 orange, it will get just scaled up to 2x comma 0. So you take a point 1 comma 0, it will go to 2 comma 0, just scaling. You take up a point minus 1 comma 0, it will go to minus 2 comma 0. It can be in any direction, right? You take up 20 comma 0, it will move to 40 comma. But what's important is not suffering any orientational change. So this is that crazy direction. Crazy direction, right? So now again search for a new direction, because we know there were two directions of that, and this we have already. So now I can tell, like, corresponding to lambda equals 3 2, we have found a direction, basically 1 comma 0. I could have given name to any direction like 2 comma 0, 1 comma 0, minus 1 comma 0. All are multiplication of this 1 comma 0 by some factor lambda, which is 2 over here. Okay, so that serves as a direction by my choice. You could definitely take 2 comma 0. So corresponding to lambda 2, we have infinitely many directions. So all apple orange pair along x-axis, lying on x-axis, will suffer the same change. So this is just a representative direction. Okay, it's always nice to take most simplest representative direction. So this represents your scaling factor, and this is a direction along which that factor was scaled. And as you can see, the thumbnail of this video is fundamentally describing this in a very nice pictorial way. Now let's put lambda equals 3 and try to do the same calculation. So if I keep lambda equals 3, again we'll get 8 times xy. Now this time I want it to be 3x comma 3. So now I want some vector to be here, Golu comma Bolu, and I want that to be scaled to thrice Golu into thrice Bolu, kind of, right? So let's see, where is that magic direction? If I keep lambda equals 3, I'll get minus x plus 4y and 0 equal to 0. And that's great. We have minus x plus 4y, minus x plus 4y equals 0, and second equation is giving 0 equal to 0. Now what does it signify? You see, this is very cool result. It shows like everything will work. Everything I am okay with, because it's a universal truth. 0 equal to 0 means whatever point you want to choose, it's fine. So it's basically redundant information. It's not telling you anything. Now x equals 4y is clearly giving you multiple answers, because I can choose y to be 1, then x will be 4, right? If I choose y to be 2, then x will be 8. So again you can tell, like, a direction of 4 comma 1 will be somewhere over here, and any vector in this direction, whether 4 comma 1 or 8 comma 2 or maybe 3 comma 12 or minus 1 comma minus 4, all will lie along this direction of y equals x by 4 line. So now magically we have found two directions. One direction was the x-axis, and another direction is the direction along y equal to x by 4. So in this wide world, we have got only two directions along which this apple comma orange pair will suffer a scaling change. So now you take up any point over here. If you react this with matrix, it will start rotating. You take any point on this y equal to x by 4, it will just scale. Similarly, so these two are the magical line of control where scaling is done. Any point apart from this line will definitely bound to suffer both twisting as well as scaling. So they will feel dizzy. This is no dizziness line, right? No dizziness line. In the language of mathematics, so again I can take a reference vector along this direction. The most simplest vector along x direction was 1 comma 0, and I can take the most simplest vector as 4 comma 1. So now we have got a final solution to our problem. Corresponding to lambda equals 2, we got a direction 1 comma 0. Corresponding to lambda equals 3, we got a direction 4 comma 1. In the language of mathematics, we call these two directions. In the language of mathematics, we call these two directions as Eigen vectors, and the scaling factor is known as Eigen value. I have not used the term before because unnecessarily it will complicate the essence of the subject. Okay, now you might ask a very simple question, and then I'll meet you in the next video. Like, what is the significance of this in their practical life? One of the interesting example is, suppose if you have a rubber band. Okay, so let's say we have a rubber band. and just you mark two lines on it. So let's say we have some line roughly 45 degree, we have got another line. Imagine you start twisting it. Okay, so once you twist it, so this twisting operation is basically an operator, right? So what operation you are doing on this rubber band? Twisting operation. So this twisting operation itself behaves like a matrix, right? And these directions behaves like the input vector. So let's say this direction, if I take something, let's say 2, 0, and this direction I'm taking, let's say 1, 4, just one practical example. So if I multiply with 1, 4, mathematically I'll get some answer. If I multiply this twisting action with 2, 0, I'll get some answer. Now practically and physically I can see after twisting, let's say I give a small twist of an angle of something, let's say 20 degree or 30 degree. Okay, and then I tried to record. So roughly, let's say if by applying twisting I gave a twist of, let's say 45 degree, and then I try to record what is the final configuration after twisting. You'll be very surprised to know, like this 1, 4, and this I'm giving you a practical example to do. It will just be a scale to maybe 2, 8, or maybe with the scaling factor of 0.5. But 2, 0 will suffer an orientation change. So for 2, 0, what's happened? It has scaled as well as changed its orientation. But 1, 4 initial and before was still in the same direction. So this represents the direction for the Eigen vector, and the scaling factor 2 is basically Eigen value. Now how practically it is used for the practical application? Because twisting vector or matrix is unknown, but you know input and output, because from observation I know, like this input I have marked 2 points on the objects by some different color. Output vector is already known. So we have 2 equations and 2 unknowns, right? Basically we have x, y, z, w, 4 equations and 4 unknowns. Okay, so you can come with the setup of the equations here. Here in this case, mostly if you see, this matrix will be, okay, in general we don't expect to be symmetric, but in some practical situation, in the real life, in the mechanics of materials, you'll see this becomes magically symmetric mathematics because of the symmetricity of universe somehow. And then you can easily get the value of x, y, z, w, either by inverse of a matrix or just by basically computing inverse amounts to just solving the linear equation system, right? So once you do this, you know the unknown twisting matrix. And now you don't have to do experiment to get the final result for any other direction, right? And that helps you to exactly track in which direction crack occurs, because there are stress theory. When you twist an object, it develops a certain longitudinal stress as well as transverse stress. And there are different von Mises theory of stress and many principal stress theory, where you know, depending upon the material, whether it's brittle or the elastic material, some material is liable to break under the longitudinal stress, and some more suffer some more drastic change in the transverse stress. So you know exactly like the point, the direction along which maximum stress occurs using mathematical setup. And once you know that, it's very crucial, because now you can save the material, mostly in aircraft designs, boiler designs, and this. So I hope like you got a full feel of this, what exactly is eigenvalue and eigenvector. So the lambda that we have obtained in this drama is known as eigenvalue, and the direction is eigenvector. And this was the entire philosophy of this. The word eigen came from the word characteristics, so if you Google it. And now it's a justification for our final image. So I'm a matrix, you give me an object, and I get a scale in the same direction without suffering any change. So this ratio, the ratio of this length is basically that amount of scaling is known as eigenvalue. So if my orientation is same for these two operators, you know that crazy direction is the basically direction for eigenvectors. So a scaled object is known as eigenvector. Their orientation is same. And then the story continues. We'll meet again with the nice correlation between coordinate geometry or the nature of conic sections, how that can